Welcome to a screencast on an introduction to chemical equilibrium. Let's start by considering the reaction of nitrogen and hydrogen to make ammonia, NH3. And if we were to have some nitrogen and hydrogen, the reactants, in a container, and they were in a situation where they could react, we might expect to produce ammonia, NH3. Now, in reality, many chemical reactions don't go 100% to completion. So in this case, the reaction of nitrogen and hydrogen would not completely produce ammonia. It would produce some ammonia, but some nitrogen and hydrogen would be unreacted or still left. Now, if the container is sealed so no materials can get in or out, and it's kept at a constant temperature, then eventually we reach a situation known as chemical equilibrium, where reaction still continues on a microscopic level or submicroscopic atomic level, but the concentrations of the reacting species and the species that are being produced, those stay constant. Now, let's consider essentially the same reaction, but in reverse. Ammonia, NH3, making its elements nitrogen and hydrogen. And essentially we could do the same thing in reverse. If we put some ammonia, NH3, in a container in a situation where it could react, it may react to make nitrogen and hydrogen. And conceivably it could go 100% to make nitrogen and hydrogen, but in reality, in most situations, it will do so partially. Some ammonia will be made, but some nitrogen and hydrogen will remain. And once again, if we have a closed container at constant temperature, we'll eventually reach chemical equilibrium. Now, we can put these reactions together because essentially they're the same reaction but in opposite directions. And so rather than writing two reactions, we simply write one reaction but with two arrows. And the arrow to the right indicates that nitrogen and hydrogen can make ammonia. The arrow to the left indicates that ammonia can make nitrogen and hydrogen. And we often use this for situations of chemical equilibrium. And in this case, we can either start with nitrogen and hydrogen, or we can start with ammonia. And when we put those in a container and allow them to react, eventually they reach a position of chemical equilibrium where we have some ammonia produced or some ammonia left from what we started with, some nitrogen and hydrogen produced or some nitrogen and hydrogen left from what we started with. And what characterizes this chemical equilibrium is that the concentrations of the reactants and the products are all constant. So when chemical equilibrium is reached, the concentration of nitrogen will be constant, the concentration of hydrogen will be constant, and the concentration of ammonia will be constant. Now, we can look at graphically what occurs if we were to, let's say, start with no ammonia in our container, and we put in maybe an initial concentration of 1 molar nitrogen and 3 molar hydrogen. And if all we have are nitrogen and hydrogen, the substances on the left-hand side of this chemical reaction, the only thing they can possibly do is make ammonia. So the concentration of nitrogen will decrease and the concentration of hydrogen will decrease. And note that for every 1 nitrogen that reacts, 3 hydrogens react. So the concentration of hydrogen will go down 3 times as quickly as the concentration of nitrogen goes down. And starting with 0, the concentration of ammonia goes up because ammonia is being formed, and it has its concentration increase twice as fast as nitrogen and 2/3 as fast as hydrogen. And then note, if we wait long enough and we have a sealed container and keep the temperature constant, eventually we reach a situation where the ammonia concentration is constant, the hydrogen concentration is constant, and the nitrogen concentration is also constant. Now, if we started with different initial concentrations of hydrogen, nitrogen, and ammonia, for example, we could start with them all having the same concentration. And depending on the circumstances, nitrogen and hydrogen may be produced, as they are in this case, and ammonia is used up, as it is in this case. Or we could start with concentrations such that the reverse occurs. But in either case, eventually we get to constant concentration of each substance that's involved. So if we do some experiments with this system of nitrogen, hydrogen, and ammonia at 450 degrees Celsius, we find the following. We can have an initial concentration of nitrogen, hydrogen, and ammonia as indicated, 0.500 molar for each of them. And when we reach equilibrium, we find the following concentrations of the substances at equilibrium. And then we do a different experiment with different starting concentrations, and we get the following equilibrium concentrations. And then we do it again, and one more time. So each time we start with different starting concentrations of the substances involved, and each time we end up with different concentrations of the substances at equilibrium. And if you look at these numbers, there's nothing super apparent in terms of any kind of consistency or obvious generalization. But if you spend a little bit of time looking at the numbers and trying various possibilities, what you find is the following. If we make a ratio of the concentration of ammonia squared at equilibrium over the concentration of nitrogen times hydrogen cubed at equilibrium, we find the following. We get 0.153 for experiment 1, 0.152 for experiment 2, 0.152 for experiment 3, and 0.154 for experiment 4. Now, these numbers are essentially the same value, certainly within experimental uncertainty, and so we have a constant value for our various starting concentrations of substances, and this is what's known as an equilibrium constant. And in general, what we find is every reaction is going to have an equilibrium constant, a constant value regardless of what you start with for your initial concentrations of substances. And interestingly enough, if you look at this, you'll note that the exponent for the ammonia is the same as its coefficient, as is the case for nitrogen and hydrogen. The exponent and coefficient for each substance are the same. And this turns out to be true in general, but specifically, first of all, for the reaction making ammonia from N2 and H2, what we find is that K sub C, this is what we use K to symbolize our what's called equilibrium constant, and it has a subscript C to stand for concentration because we're using concentrations of substances. It turns out that that ratio is a constant value for a given reaction at a given temperature. And it's a ratio of what we've typically been calling products, but now we're going to just call the substances on the right-hand side of the equation over the quote-unquote reactants or substances on the left-hand side of the equation, and they're going to be raised to the power that corresponds to the coefficient of that substance in the reaction. And for a general reaction, a generic reaction, A and B being reactants and C and D being products, and M and N being the coefficients of the reactants and X and Y being the coefficients of the products, what we find is that the equilibrium constant expression is K equals, and if we're doing concentrations, K sub C, concentration of one product to its coefficient as a power, second multiplied by second product times its coefficient as an exponent, and if there were more products, we'd continue that process. And then for the reactants, same idea, but they are in the denominator. And we should note, if we're dealing with gases, we often do equilibrium constants in terms of pressures rather than concentrations. And then we'd have a case of P, or a pressure equilibrium constant. And the format is the same, but we use pressures rather than concentrations in molarity. Now, a couple other things to note. The equilibrium constant is specific for a given reaction. It depends on how you write the reaction, and it depends upon the temperature at which the reaction is or takes place. And if we have an equilibrium system with some pure liquids or pure solids in the system, then we don't include the pure solids or liquids in the equilibrium constant expression. This is a convention we use, and it's because pure liquids and pure solids have constant concentration, so their concentrations aren't changing, and so we leave them out of the equilibrium constant expression. And that's it for an introduction to chemical equilibrium.